All right, man. I'll tell you what, everybody. Laurel, hey, good to see you online. David Englehart. Oh, here we go. Here we go. What do we got? Good morning, all. Soon after the Eastern Time Zone, presumably by the time. Yep, soon to be afternoon. It is 11:32. I went 11:30 just because I wasn't sure how long I was going to have to go. David, man, we're gonna have fun today. Whoop, there it is. The man of the hour. Steve is in the house. Excellent. And then finally we have Laurel online. She's going to keep us honest and check all of our references. Thank you, Laurel, for joining in. All right. So I had three questions. Hold on. I don't know which screen. I got a cam link. What the heck is that? That's for. All right. I don't know which screen is going to be there, but let's do this. Oh, me and monitor. Cam A, monitor A? Nope. Cam A, monitor B. There it is. So I had three. I have another one that I had actually two that came in, if we can get to them. The first one was the individual asked for the math on how three-phase currents add up to zero in the neutral. So complex variables, that is what we're going to do in this one. So remember, three-phase, all three phases are, all three phases, and I was having a hard time, which is why I was like a minute or two late. I was having a hard time with my iPad, so I spent more time trying to get this iPad to connect than I did to try to prepare. So when you think about a three-phase system, you have one. Actually, this is the way I like to draw it. So I'm going to do this. Oh, let me do this. I'm going to go to template settings, and I'm going to get us some lines. What do you guys think? I like lines. So let's do this. Let's draw. And I'm going to do a thicker line. I'm going to draw. Boom. Boom. All right. So I have an axis. I've got, I'm going to use, will red show up? Yeah, red will show up. So I'm going to use red for my thingamybobs. So if I start from zero and I say I have a vector along the zero axis, so one phase will have 0 degree. It's our reference. I'll call it our reference. This second phase is going to have a 120 degrees. Now remember, from here to here is 90. If I take, I'm sorry for my cough. I don't know what's going on. I've got some stuff going on in my throat. If I take 360 divided by 3, I get 120. So evenly spaced apart, I can look at that as this angle, a minus 120 degrees. I could also look at it at, if I do this all the way around, that's 240, right? So angles, when I start doing my functions, my cosine and sine functions and things like that, the angle, whether I use 120 or 240 or minus 120 or 240, will work out in the end. But what we're going to basically get into is, I'm going to take that one out. That's basically our picture, is I have vectors. So whenever we think about the math associated with a three-phase system, I represent, whether it be a voltage or a current, as what I call a vector. So what is a vector? It's not something from sci-fi. A vector is a magnitude at an angle. So if I think about these three, if I said this was 100, and this is 100, and this is 100, and let's say this is A, and this is B, and that is C, A, B, and C. Should have drawn it a little bit smaller. Hold on, I gotta figure. I know I have a, there it is. Nope, that's not what I wanted. I want to mute so I can cough. There we go. I've got to put a mute button on my thing. So I have basically three vectors. I have A, B, and C vectors. So phase A is 100 at an angle of 0, because that is 100 and my angle is 0. That's my reference. My phase B is 100 at an angle of 120, right? So there's 100. My vector is 100 at an angle of 120. Capiche? Oh, dadgummit, 100 at an angle of 120. I was trying to get rid of that and doing the back thing. All right, so then phase C, what's phase C going to be? Now, I could say phase C is 100 at an angle of 240 or an angle of minus 120. I'm going to say minus 120 because I'm going to reference everything to my phase A. So we're going to say that's 100 at an angle of minus 120. And I know this is not very clear. All right, so I've got my vectors. These are vectors because I express a vector at a magnitude and an angle. We call these polar coordinates. All right, so those are polar coordinates. I can also represent each of these vectors in a rectangular, I couldn't think of the word, rectangular coordinates. So what are rectangular coordinates? If I come back up to here, and let's say I focus in on phase A. Remember, a rectangular coordinates. Rectangular coordinates are going to be expressed in x plus J represents the imaginary, J represents this, the y-axis. So it's x plus jy. So if I think about, Robert, good morning. Good to see you, brother. Glad you are able to make it. Thank you for coming in. So if I think about rectangular coordinates, I'm basically saying I can take this phasor, this polar coordinates of 100 at an angle of 0, and I can say that this is, along the x-axis, it's 100, we know that, plus j0, because it doesn't go on the y-axis, it's 0. So it's 100 plus j0. 100, I'll call this, let's do this. I'm going to zoom in, and I'm going to draw a power triangle. So this is my R. I'm just going to say this, my power triangle, this can be R, X, and Z, or it could be P for real power. This could be VARS, and this could be VA. All right, so I use the same triangle for both. If I told you for each of these, I have, for the first one, remember my vector, and this is theta. So if this was 100 at an angle where theta equals 0, what would that look like? I'm going to delete that. I'm going to delete this. 100 at an angle of 0 looks like that, right? So my x is equal to 100, my y is equal to 0. So those are the polar coordinates for my x, and there's a reason I'm going over this, because it's going to be very important as we move forward in doing our calculations. Right? All right, so what was the other one? The other, so that was, so remember, I can represent, so phase A, let's do this. Phase A is equal to 100 at an angle of 0 is equal to 100 plus J0. That's the polar and the rectangular. Now I got to do phase B. Phase B was 100 at an angle of 120. Now what is that equal to? So if I go back to my triangle and I say my angle now is 120. Now I need to get, I'm an artist. I know, I'm going to put that up there because Art by Tommy D. So, Carl Lewis, yes, I have seen phasers since college. In fact, I would argue that I use, put it this way, I haven't seen Laplace transforms and differential equations since college, but I have seen complex variables considerably. Now, what I need to do now is I need to figure out, I know that I'm 100 at an angle of 120. And this is a good example of where I use these complex variables since college. So what I need to do now is I got to think about my cosine and sine functions, right? I'm just answering. I got multiple things going on at the same time. All right, so I'm just answering. I got too many things going on at the same time. All right, here we go. So what we know is, let's think about the cosine and sine functions, Carl, and tangent, right? So let's come down here. What about integers are under the sine peak? Integers, the sine peak. Remember, we're dealing with three-phase circuits, and we're dealing with three-phase circuits. Robert, and we're dealing with three-phase circuits. We're not dealing with the individual sine wave details. So that's an important distinction to think about. I'm going to move this over here so that I'm not looking that way for you. All right. All right. So what we know is that if I think about a triangle, remind me of the second year electrical apprentice and right angle. Yeah. Yeah. Yep. That's what this is. That's what this is. It's all trigonometry. So if I know the angle, so I know that if I know the angle, I don't know, and I know what? I know this. I know this is 100, right? So I know my magnitude of my vector is 100. And then I know it's 100 at an angle of 120. So I know the hypotenuse. Now, tangent. Remember what tangent is. Tan of theta. No, I'm sorry. Cosine. Cosine. So if I did cosine of theta equals, equals what? Opposite, adjacent. Adjacent over hypotenuse. Sine theta is opposite. Make sure I got this right, guys. I always screw this up. So cosine of theta is adjacent over hypotenuse. Sine of theta is opposite. This would be the opposite. This is the adjacent. And this is the hypotenuse. Because it's opposite of where the angle is. So if I wanted to know what x was, so we'll call adjacent x, and we'll call opposite y. Let me do this. I don't want to lose this. Copy, and we're going to bring this to somewhere new. Right down here, because I feel like I'm working in a corner. All right, so we have a triangle. We know that cosine, oh my goodness, man, I'll tell you what, I am a wreck here. Cosine, geez. Cosine of theta equals x over 100, right? Because that's the hypotenuse. Sine of theta equals y over 100. All right? So if I want to know what x is equal to 100 times the cosine of 100 times the cosine of 120. Right? So x is equal to 100 times the cosine of 120. Y is equal to 100 times the sine of 120. Let's see what those equal. I will do it on my iPad. If I can find my calculator. Where is my calculator? There it is. I don't know how many of you use reverse polar notification. Thank you. And sine equals cosine over tangent. All right, so let me go back to this. 100 times cosine of 120. So if I say 100, 120 cosine times, it's minus 50. So x equals minus 50. Y is 100 sine 120. 100, 120 sine. And I do times 86.6025. 86.6025. All right, so what that tells me is, if I come back up to this, I know that if I draw this down, That was minus 50. And if I draw this over, this is 86.6025. 86.6025. Do we agree? Hold on. I'm seeing some. Oh, Carl. Will there be questions like this on the PE power exam? Oh, absolutely. You have to know this for the PE. I'm not going to say there are exact questions like this. All I can say is you should have this as a fundamental. You need to know your complex variables. Very important to understand the triangle, the whole bit. Do. 0.866, Robert from Omaha. Sine equals, okay. It's a great benefit, Carl, to understand the angles and the graphic expressions, polar plots, as it helps to understand the physical reasoning of electrical theory. Yes, and the way it works. I'm going to bring this out, and I'm going to bring this up. There we go. Now, see, look at that. We're rocking it here. All right. Hey, Felix Sandoval in the house. True, I have seen phasers since I graduated college, but I'm sure they'll will be on the P. Yes, it will. Excellent. All right. I don't want to blow yours out. All right. So now we know the phasor. So we have the polar rectangle, polar, and we know that the x-axis is minus 50, and the y-axis is 86.6025. So we know now. Let's do this. All right. So we said this was minus 50 plus j 86.6025. 86.6025. Now you know whenever I'm dealing with the real and reactive, that's the x and the y. That's all it is. And we're dealing with standard stuff you learned in high school on how to deal with a transform, how to deal with a triangle. All right. So now phase C is 100 at an angle of minus 120. Now we got to do the same thing. We know that what we're dealing with is, do this here, x is equal to 100 times cosine of minus 120, and y is equal to 100 times sine of minus 120. All right. Oop. So 100, 120 negative, boom. Oh, 120 negative cosine times, boom, minus 50. So this is minus 50 plus j. Sine of 100, bam, 100, 120 minus sine times minus 86.6025. Minus 86.6025. So this would be a minus j, 86.6025. All right, so that's because it's minus. Now I'm going to erase, and now you're going to see why I did it in rectangular. Because in rectangular, fundamental rule. Rules. Rule numero uno. Adding complex variables. Add the reals. Add the imaginaries. There's your real and your x, and that's your new value. You have to convert polar to rectangular. Now, that's if you're doing it the way I'm doing it. I could just get a calculator that I can put 100 angle 0 plus 100 angle 120 plus 100 angle minus 120, and it'll do the math for me. But if you want to understand how to break it down, which I would highly recommend, especially for the PE exam, I would highly recommend you break it down to real and reactive, X and Y axis. Add all your X's, add all your Y's, and that is adding all three of those together. Because if you think about a three-phase system, right? You think about a three-phase system, and let's say I had a load. I'm not the best artist, I'll tell you that much. And there's your neutrals. All right, so V, V, V. So each of these phases are going to be out of sequence with each other, or out of 120 degrees separated, right? So all the current that goes down this way, so this is IA at an angle of 0. This is IB at an angle of 120, and this is IC at an angle of minus 120. Capiche? Right? Now, what we could do, I'm showing you how they add up to 0. I could do another session and just say, look, what happens if my voltages are at angle of 0, angle of 120, and angle of minus 120, but my loads are real and reactive. And they're different. Ooh, they're different. We could do the same math, all right? We'll do the same exact math. Michelangelo has nothing. I know, Michelangelo has nothing on me, baby. Right, so let's go back up to this now. Now, so if I want to know, if this was, say this was I phase A, I phase B, I phase C, and they were 120 degrees apart. And I don't care what the numbers are. I could say 0, 120, minus 120. I could say 30, and as long as I'm 120 and 120, my starting phase angle doesn't matter. As long as they're balanced 120 degrees apart, it'll all work out in the end. So if I want to add these up, so what is 100 plus minus 50 plus minus 50? 0. What is 0 plus 86.0625? Minus 86.0625 is 0. So they add up to 0. And the reason they add up to 0 is because they're balanced. They are 120 degrees out of phase with each other, and the magnitudes are all of the same. Now, let's say, for example, it was 100 and it was 70 and 100. Let's do that. Let's do that. 100, 70, and 100. Okay, so we have phase A is equal to 100 at an angle of 0. Phase B is 70 at an angle of 120. And phase C is 100 at an angle of minus 120. So we know how to do the math. We break this down into real and reactive. So this is 100 plus J 0. This is 70 times 70. 120 cosine times minus 35, minus 35. So minus 35 plus j, and I know it's going to be plus. Why do I know it's going to be plus? Because I'm this way. So 70, 120 sine times 60.6218. 60.6218. And then I'm going to do this one, 100 minus 120. 100, enter, 120 minus cosine times minus 50. Minus 50 minus j. And I know it's going to be minus because I'm this way. That's why I always, and you got to be careful when you're doing the sines and cosines, because if you don't, at least I do. I have in the past, I have, watch, I'll show you, sine times 86.6025, 86.6025 minus 86.6025. Now let's do this. Let's say that I did 100, and I did, instead of minus 120, I did 240 sine times, still minus 86.6025. So you get the same number whether you are minus 120 or over the out of the way. All right, so, but if somebody just told you an angle and didn't give you whatevers, I'm not going to get into that. All right, so now if I want to know what the resultant is, 100 minus 35 minus 50. 100, 35, 50. I'm at 15. So this is 15. Then I'm at 15 minus 60.6218. 60.6218. Enter. Minus 86.6025. 86.6025 minus. Minus 25.98. Minus 25.98. 25.98. Now, if I want to know what the, now that's the resultant. So where's that going to go? It's got to come back in the neutral. Now, if I want to know what is the, so what do I know? This is what I know. I know this is 15, and I know this is 25.98. I don't know the angle, and I don't know the hypotenuse, right? So if I want to know z is equal to 15 squared plus 25.98 squared, and I do the square root of all of that. 25.98 squared, 15 squared, crap, 25.98 squared, 15 squared. Add those together, square root thereof is 30. We'll call it 30. We'll say this is 30 at an angle of, so I can do a couple different things. I can take, remember what our numbers were. Boom, boom, boom. Cosine, where's cosine? Cosine theta is adjacent over hypotenuse. So adjacent over hypotenuse. So 15. So cosine -1 of 15 over 30 is equal to 15. 15. 15, 30 divide, inverse cosine. So I have to use that, and I go to A cosine. Boom. 60. Angle of 60 degrees. So that's what I have in my neutral. When I have an unbalanced, so I have 100 amps going out at 120 degrees phase angle difference. I only have 70 going out on phase 3, and my difference is 30 at an angle of 60 coming back over the neutral. So what I just did was I gave you a, if you watch that over again, and I gave you the fact that we're 120 degrees apart. I started with the amps, and I just changed the angle. Or I didn't change the angle. I started with the amps, and I kept the angles the same. What you could do, which what you could end up doing if you wanted to, you could say, look, I have 208. Is that 208? I think it is. Let's do this. No, no. I won't do line to line. I'll do 277, 277, 277, 277. Angle of 0, angle of 120, angle of minus 120. Okay, and then we say we have this and this, this and this, this and this. All right? So what you could do is you could say, look, I'm going to have, I'm going to say this is 10 plus j, I don't know, 5. This is 10 plus j, 5. And this is 10 plus j, I don't know, 2. Okay? So you can have your, come on, JP. You can have your real and your reactive. You can have your real and your reactive, and then calculate IA, calculate IB, and calculate IC. Right? So you can calculate based upon the impressed voltage what the IA is and what its angle is, and that use the same math that we just did. I mean, you know that, let's do this. Let's say that you had 277 angle of 0 over 10 plus j5. So it's 277 angle of 0 is being a, 10 plus j5 impedance, right? So now, rule number 2. Rule number 2. When multiplying or dividing complex numbers, use polar coordinates. And remember, this is polar, angle of 0. So what you would want to do with this is you'd want to convert this to polar. So this would be a magnitude, 10 squared plus 5 squared, square root of 10 squared, 10 squared, 5 squared, add square root 11.1803, 11.18. So this is 11.18 at an angle of I should be able to take 5 over 10. What's tangent? What's the tangent equation for tangent? Tangent is equal to opposite over adjacent. Oh, man. I just want to double check. Tangent is, I think, opposite over adjacent. Or is it adjacent over opposite? Come on, guys. What is it? Do. Tangent. Tangent is opposite over adjacent. That's what I thought. So it's opposite over adjacent. So inverse tangent of 5 over 10 is equal to 5, enter, 10, divide, inverse tangent. Yep. Thank you, Eli Markovich. 26.56, 26.565, 26.565, 26.565. And how do we check that? So this is what we know. We know this is 11.18 at 26.565. And now, how do I know if it's a plus or a minus? I know I am real 10 plus, and I'm plus 5. So it's a plus. Okay, so it's 11.18 at an angle of 26.565. If I want to check that, I could take, I could go back to my 11.18, 26.5. I do a cosine 11.18 times, and that's 10. So that's my real number, which is where I was. So I know that number is right. So you can always check your math. I couldn't remember if it was opposite over adjacent or adjacent over opposite. It's opposite over adjacent, so inverse tangent, blah, blah. I'm good. All right, so I have 11.18 at 26.5. Now, so I know this is 11.18 at an angle of 26.565. If I want to, I'm going to do this. I'm going to delete, because I'm going to go back to all of what our premise was. Cut. So multiplying or dividing complex numbers, I use polar. If I'm multiplying, if I'm multiplying, I multiply magnitudes and I add angles. If I'm dividing, I divide magnitudes and I subtract angles. So if I wanted to multiply 277 at an angle of 0 by 11.18 at an angle of 26.565, is it 565? I erased it. Then I would multiply 277 times 11.18 and I would add 0 and 26.565. And that would be my resulting. Now, what I would be doing here to determine current, I need to take 277 angle of 0 divided by, V is equal to IR. I know my voltage. I know my impedance. To get I take V over the impedance. So I take 277 at an angle of 0 divided by 11.18 at an angle of 26.565. And that's equal to 277 over 11.18. 277 over 11.18. Divide 24.78. So that's 24.78. And what I take is I take my 0 at an angle of 0 minus 26.565. And that is equal to 24.78 at an angle of negative 26.565. Capiche? So that would be the current I in phase A. And so what you would do, if I go back up to our little diagram, I would calculate the phase current A, calculate the phase current in B, which A and B should be pretty much all the same math. Now C is 10, has a different angle to the load, 10 plus J2. You would add that separately and then convert those all to rectangular coordinates, add your reals, add your imaginaries, add your R's, add your X's, add your X axis, add your Y axis, and that will tell you what's in the neutral based upon a balanced voltage, sources, and loads that are of different power factors, basically. That's the impedance of the of the load. And you'll get different currents at different angles, and then add those up. That'll tell you what's in the neutral. Make sense? All right. I got to go back. Let's go back to our what we do. Okay, so is there... Oh, I got to go back up. Boy, we got Robert. We got... Man, you guys are answering and asking. True, I have seen phaser since I graduated. Yes. Yep, it'll be on the PE. Good morning. Hey, Felix. Thanks, Robert. Michael Angelo has nothing on me. I saw that one. That was a good one. Is there a calculator you recommend that you could do these phaser calculations quickly on the PE exam? Yes. Well, I'll tell you what. Man, it has been that long. I used to carry this calculator with me all the time. Because you probably can't use your... I don't know if you can use your phone anymore. I gotta find my calculator. Let me find my calculator. Here we go. It doesn't have batteries. At least if it does have batteries, I will be shocked if it actually works. But this is the one that I use. I need new batteries. It takes two. It takes two to tango. And I'll tell you the battery it takes is CR2032. It takes two CR2032s. I need to get these out so they don't... All right, so I'll tell you, this is what I used and I still use. Oh, hold on. I gotta put this back in autofocus. That's what I use. I don't know if you can see it. It's an HP 35. HP 35S scientific calculator. That's what I use. It's really been good to me. I love this calculator. It has a lot of... You can do things in polar coordinates, so you can just add them up easily. You can do them in rectangular coordinates. You can add a rectangular coordinate. It will automatically convert it to polar coordinates. But on the PE exam, that is what I used. You'll see all the different buttons on it. That'll get you everything that you need. So it's an HP 35S. I'm sure they still make it. It is, in my opinion... But again, it's, Texas Instruments has probably a very good one as well. I like the RPN. the reverse polar. So coordinates, and I got to get 2 of those. So in any case, now the other thing I do use is this is a 42S. And I don't know, I've not done, there's a complex. So complex, look at that, there it is. So there's your polar, there's your rectangular. So I could say 100, 100, 100. No, hold on, clear. 100. Oh, that's it. So if I want to do 100 at an angle of 120, I do 100, 120, and then I hit the angle. Boom. That's 100 at an angle of 120. And if I want to say, I want to add 100 or multiply 100 at an angle of 0, complex. So there's my, oh, shoot, I'm not showing it. Hold on. There it is. So I've got 100 at an angle of 120, 100 at an angle of 0. And if I hit plus, it tells me I'm at 100 at an angle of 60. Now if I do 100 at an angle of 120 negative, and I hit complex over there by STO on the side, now there's my, and I hit add plus, it comes up to 0 at an angle of 0. So with this type of a calculator, you can add things in polar coordinates. What I showed you was how to convert polar coordinates over to rectangular, and then you add your x's and add your y's, and then convert it back over to polar coordinates by using the complex variables. Okay, so you can do this on a calculator. My opinion, this is what I would do, and I would urge you to do this. Do some hand calculations. Do them on paper. Write out your problems like we were just doing. Do it by hand, and then verify your answers using the calculator. What that will do is it will give you the moxie that you need to be able to handle anything in the future. If you just went straight to this and somebody gave you rectangular coordinates, you would be lost. So do them both ways until you feel very comfortable. And then even after that, like I'm doing now, I haven't done this in a long time. So in fact, I had to think about what was tangent again. Is it is tangent opposite over adjacent? Is it adjacent over opposite? I had to think about that. And you could verify your numbers, but if you understand how to derive it, you're better off. All right. So and then it will let you do. So that's complex. I don't know that this app will let you do rectangular coordinates. I know my calculator has a rectangular coordinate in there. I don't believe that this does. I'm just looking through all the red or orange numbers. I'm not seeing it. All right, so, but in any case, that should answer that question. Okay, so symmetrical versus non-symmetrical, completely. So here, man, Robert, you had to do that, didn't you? So what we do for that is left for a different day, because the moment you start to get into the discussion of symmetrical versus non-symmetrical, etc., I automatically go to got people going back and forth. So I automatically go to symmetrical components. So there's a good textbook that I have, Wagner and Evans. does symmetrical components. It was symmetrical components was created by Mr. Fortescue, C.L. Fortescue. You can find his original IEEE paper where he came up with the concept of symmetrical components, and he separates it into positive, negative, and zero sequence. That is a discussion for a different day and probably different days. But we use symmetrical components, and you probably didn't realize it. Zero sequence are all in phase with each other, and zero sequence currents is basically your ground fault currents, right? So that's why what we'll say is, and you'll hear me say this numerous times, I've said it, if I have a delta Y ground transformer, ground fault currents on the secondary don't pass through the primary because the zero sequence currents will circulate in the delta. Basically, it'll look like a line-to-line fault on the primary. So you're getting, when you talk symmetrical versus non-symmetrical, etc., you're getting into complex. You're getting into symmetrical components. And what we just talked about here is very much related to breaking down symmetrical components, but I'm not going to go there. Not today. Happy Friday. Yes. And you know what tomorrow is? Does anybody know what tomorrow is? Tomorrow is a very special day. Let me know if you know. Does Eaton make 2-pole GFCI breakers that are 22K AIC? I believe we do. Eaton GFCI 2-pole. Excuse me. Excuse me while I kiss this fly. Help me. Okay, where's it at? GFCI breakers, right? GFCI, reliable. We are reliable, resolution, blah, 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 blah. Man, you know what? I thought I would be able to find it real quickly. Let me just do GFCI. I'd have to just go up to my GFCI circuit breakers. BRN 120, Eaton. We may, that says 10K. So I think we series rate, our breakers beyond 10K. I believe I would have to double check that. I'm just looking at our models. If I go GFCI circuit breakers, here, I'm searching for it. Hold on. So if I did my GFCI circuit breakers, 2-pole, 22KA, yeah, we make them. There they are right there, Willie. Just tell them Tom sent you, and I would ask them, I would tell them, please make sure Tom gets 10% of that order. All right, so we make them 22K, make it happen, and get that breaker on order, Willie. Steve, TI-36X Pro. So see, Steve's a TI guy. I'm an HP guy, and now you have recommendations of both products. Felix, opposite over adjacent. Yes, thank you, Felix. SOHCAHTOA. Sacagawea. Good acronym to help remember TRIG. Oh, yes. You know what, Eli? Somebody had told me that. Cosine, alternate over hypotenuse, tangent, opposite over adjacent. Yeah, SOHCAHTOA. I remember that. Perfect. Carl, you're welcome. Laurel. Yes, repetition is the mother of retention. You're absolutely right, Laurel. I never thought about it that way. And exercise as many Here's the other thing: is exercise as many senses that you can. So you can remember that if I think it, if I write it down, all that good stuff, if I can see it, see it, think it, if somebody can say it to you, all that stuff. So just, you know what to do, Laurel? You just take this video and you play it over and over and over when you go to sleep, and you just listen. It'll just go in there via osmosis. And then when you get up, write down the equations and do the math. And now you will have the audio, you'll have the physical touching the paper with the pencil, the whole bit. Yep. Carl, I remember doing these calculations in AC circuit in college. Yes, absolutely. They are tedious. They are tedious. And here's the thing. They are very worthwhile doing. And make sure, I know I've done some videos in the past. Forget about those decimal points and all that stuff. And if you screw up the Sokotoa, whatever that's called, right? Chris Foland in the house. We said we were not going to do this without Chris, and here he is. Just, they are tedious, but I'll tell you, it's worth doing. Use it or lose it. I like it, Robert. My question of the week: does a wire jumper for a bus bar circumvent SCCR if bus bar, say, it was 10K and trying to get a higher... Does a wire jumper for a bus bar? You know what? I'm going to save that one for next week, Steve, and here's why. I need to understand that question a little bit more. And I have a couple more questions that I've got to go over. What time is it? It's 12:34. Okay. I'm going to put that on the list, Chris. Here, how do I copy? Do I copy it over here? Where are you at? Or Steve. There it is. I don't know if I can yes, copy text. There we go. And I'm going to put it in my notepad. Questions. I have a little running thing. Q&A Fridays. Control V. Steve. There it is. All right. I will make sure I hit that one. We got back to college and the core of our engineering. Yes, that's the core. You know what, Felix? You can't get any more fundamental than complex variables from a power systems engineering. Well, we are great. We are so happy to have you, Chris. Really glad you are here. Don't forget to like and subscribe. See, Laurel, this is what I count on. Excellent. Thank you. I never ask for that stuff. Hey, Tom, another question. When would someone use a UFER ground? Whenever it's available. So, Carl, here's what I've always, this is what I've learned, and I don't know if anybody else has a good feedback for Carl, but what I've learned is that if it's there, you use it. Okay? So if the UFER ground is there, then you use it. If you've got your rebar in that cement, stub it up, use it. And there were some recent changes, but you know what I'm going to do? Carl, I am going to copy that, and I'm going to add that to my list as well, because I'll do some homework. I know they just had some discussion about what happens if you show up on the job site, they poured the footing, they have the raceway and everything, conduit, all the rebar in there. What happens now, right? Do I have to dig up the concrete, all that good stuff? So they just made some changes, and I think it's in the 2026 code. So that discussion is pertinent. I'll do some homework for you, Carl. Hopefully you don't need to know today. If you do, shoot me an email. Go out to thomasdimitrovich.com. You'll see my contact me there. Steve, perfect, cool, thank you. It is, if it's present, you must use it. Yes, it is. That is true. But Robert, I don't believe there's a code requirement that says thou shalt create a UFER ground. So be careful that UFER isn't concrete with vapor barrier. Absolutely. So there's criteria. Absolutely. So let's get back to this. The second question, do you have a video Do you have a video explaining why you need secondary protection on a Y delta transformer? The chart is misleading as it seems the only time you cannot have secondary protection is a single voltage output. So confusing for us untrained people. Okay, so let's talk about primary and secondary protection on a transformer. Let's do this. I'm going to do a new screen. So, so we have a transformer, right? And we're going to need a primary and secondary. Now, there's different ways. You can have a three-phase delta Y ground. You can have a single phase. There's no delta or whatever in a single phase. You can have a three-phase delta delta, Y Y, etc., etc., etc. So, what I would, if you asked me from a code perspective, there's a few places that you would go to. From an NEC perspective, a good place to start. Where is a good place to start? 240? 240, location in the circuit of your overcurrent protection. 240.24? No. Is it 240.21? 240.21, location and circuit. If you go to location and circuit for the overcurrent protection, there is a part C. My reference here would be 240.21 first level subdivision C, which is titled Transformer Secondary Conductors. Because the big question is, that I think is what everybody, if you think about this transformer has a what we call transformer secondary conductors, right? Delete. Cut. Okay, so the transformer has a transformer secondary conductor. So transformer secondary conductor. And the question is that conductor protected from the primary overcurrent protective device? Now, when I say, what do I mean by protected? I'm talking short circuits, and I'm talking overload. I don't think anybody would argue that this transformer secondary conductor is protected from overload because of that device. Right? An overload, all of the current stays in the path. So if I have an overload in this, if I'm in overload, all of my current is still passing through that overcurrent device as long as this OCPD is sized at the ampacity of that transformer secondary conductor, then I'm golden. I'm going to protect that conductor from overload. But I can't protect if I have a short circuit right here, and let's say that that is a ground fault. If I have a ground fault on the secondary of a transformer, of a delta Y ground transformer, the primary OCPD will not see the secondary fault. Ground fault current. Why is that? Because we said it earlier. Ground fault currents, ground fault amps circulate in the delta. They won't pass through. It'll look like a line-to-line fault, but I can't tell you the magnitude. So, if you ask me from a technical, based upon what we're doing, there are various reasons why your ground fault, your primary overcurrent device will not provide the protection. Short circuit protection is what we're talking about. Now, if I go to Article 240 in Section 240.21, what it says is right here. It says that conductors supplied by the secondary side of a single-phase transformer having a 2-wire secondary or a 3-phase delta-delta connected transformer having a 3-wire single-voltage secondary shall be permitted to be protected by overcurrent protection provided on the primary side of the transformer, provided this protection is in accordance with 450.3 and does not exceed the value determined by multiplying the secondary conductor ampacity by the secondary to primary transformer voltage ratio. Single-phase and multi-phase transformer secondary conductors are not considered to be protected by the primary overcurrent protective device. So unless it is a delta-delta 3-wire or a single-phase 2-wire single-voltage secondary, unless I meet those two conditions, then I cannot claim that the secondary will be protected by the primary overcurrent device. See 450.3 also. Let's check out 450.3. So now what we're doing is we're giving you the code reasons why 450.3 is overcurrent protection of transformers have to comply with A, B, or C. A is your transformers over 1,000 volts. B is transformers 1,000 volts nominal or less. And remember, the tables in 450 only apply to protection of the transformer. They don't apply to protection of the secondary conductors. So, for example, if I go to 408, if I went to 408, 450, you can have primary only protection, but that only applies to the transformer, and it has to be set at low enough to provide both short circuit and overload for the transformer itself. Doesn't have anything to do with the transformer secondary conductors or secondary equipment. If you go to 408 as an example, and you go to panel boards, and you look at overcurrent protection in 408.36, there's some specific language in there that speaks to supplying when you have a panel board that is supplied on the secondary of a transformer. Where a panel board is supplied through a transformer, the overcurrent protection required by 408.36 shall be located on the secondary side of the transformer. And the only exception is that 240.21C1 when you have that single phase or delta delta. So you have both of those instances. Really, you got to go to other areas to ensure you have protection of the conductor on the secondary and the equipment that is on the secondary. Wouldn't the secondary fault current increase the primary current? Sure, it will. It will increase the primary current by the turns ratio. David, I would agree with that. Absolutely. Hey, so you're back up in the sky. So you've left, where were you? You were in, wasn't Hong Kong. You were in Korea. Weren't you in Korea? Seoul? I think you were in Seoul, right? Nihad, super late to the game, but you're in the air, baby. That's awesome. We've now covered, we are international globally and in aerospace. So thank you. Don Ganir says the primary OCPD will see the current from the secondary ground fault as the overcurrent is supplied by the primary winding, but won't know that it's a ground fault. Yes, because it won't be a zero sequence. It may or may not clear based upon the OCPD. I agree with you 125%. You're over the Pacific Ocean. Nice. I hope your flight goes over well too. Too many code users confuse the rules in 450.3b and 240.21c. Absolutely. Both have to be complied with. However, on the secondary side, a single OCPD can meet the requirements of both code sections. Absolutely. If you put a overcurrent device on the secondary and 408, can't forget about 408. Can't forget about what it is you're protecting on the secondary. Very good. Sorry about coughing. Okay, so I think we hit all of the right code sections. So hopefully you have that covered. What time is it? It's 12:50. I can't even remember what time I said I was going to go to. 1 o'clock. So, man, we started at 11:30. All right, 12:50. Let's read this one. I think it's this. There it is. So, this gentleman says, "Good morning, Tom." Good morning. It is afternoon. Hope all is well with you and your family. I know you're a busy guy, and I'll be brief. I have a contractor that experienced an interesting issue with a 170 amp branch breaker feeding a PV inverter. The available fault current ratings were calculated to be below 65,000 amps. The overcurrent device and the inverter were rated above the maximum available fault current at the transformer. The overcurrent device and inverter were rated. All right, so that means all of our equipment is within its ratings. However, the breaker shows signs of carbon dust in the vent ports. Ooh. Would this be normal and the overcurrent device is okay to put back in service? Question mark. Did the overcurrent device fail and should be replaced and sent back to the manufacturer as defective? Question mark. Just looking for thoughts. Thanks for your time. Also, you're doing a great job. Oh, thank you, sir. Keep up the great work. Awesome. All right. You know, I felt like, remember when Ralphie was reading the letter, from, he was waiting for his decoder ring and everything. Remember that? That's what I felt like. Anyway. All right. So here's my thoughts on this. There is a good document, NEMA AB4. Look, it automatically comes up, and I've accessed it before. I would go to the NEMA website. I would say, let's do this. How do I do this? Let me show you something. All right. All right, so guidelines for inspecting and preventative maintenance of molded case circuit breakers used in commercial industrial applications, which is exactly what you've got. It's a free download. You can click the button. You can accept the downloads. Boom, you just saw it go into my little box here. And then I bring it on up to the east side, to that deluxe apartment in the sky. All right, so this gives you some really good, I would fall back on this document. Let me search for, what was the question? He said vent ports. Now, Control F, vent. Oh boy, that was a mistake. The exhaust vents must not be blocked. So you want to remove, so there are things you can do to that circuit breaker. So here's what first thing I would say, sounds like all of the ratings of the equipment are above the available fault currents. We don't know exactly what fault current was interrupted by that overcurrent, that circuit breaker. So he noted that the breaker shows signs of carbon dust in the vent ports. So I would say you open them, you would want to do what this is saying. You would want to do what this document is saying and make sure that those vent ports are not blocked. All right. Vent ports, dust, carbon. Let me just do carbon. There's no carbon in there. So if you read down through this document, I'm trying to make this shorter because I got like I don't know, a couple minutes. So what I would suggest is that you take that circuit breaker, because A, it was a short circuit, it's a fault, it's not an overload, so you're not sure what currents that circuit breaker interrupted. You've already said that you've looked at it at the vent ports, and there's soot or whatever, carbon dust. Be mindful that anytime a circuit breaker opens those contacts, it will vent out those ports. They have, even a molded case circuit breaker. I used to have product sitting in my drawers. I don't know if I have a clear, oh, do I? Nope. I have this. Yeah. This is the very first Series C circuit breaker. It's not even a circuit breaker. That's what they used when they came up with the design. Looking to see if I have something that has the ports. So yeah, okay. So here, this is an oldie but a goodie. Some of you may be familiar with these. Remember these Pushmatics? Remember that? They called these things Pushmatics. Now, even these, think about, this is how many amps? I don't even know what amps it is. Do not use electrically. But let's take a look at the very bottom. You see down there in the bottom? Right in here? Right there, and on this side, right here, you see these little slots? Any circuit breaker is going to have an exhaust area where where it vents any of the gases from the arc. There will be, in some cases, you'll have an arc extinguisher. And I used to have an arc extinguisher in my drawers, but I don't have an arc extinguisher. They're all back there. But they would have arc extinguishers. And I have to keep these things in my drawers. I got to keep a little sample. I got to keep my sample going. So the arc extinguisher. So what happens with an arc? The arc goes across these plates like this, and the arc goes up in between, and it cools the arc. Well, there will be gases that are expelled, and those gases have to come out somewhere. Now, just because you see some of the venting doesn't mean that the breaker is no longer functional. It doesn't mean that it didn't do its job. It doesn't mean that you need to replace it. I would argue that you probably want to do some maintenance on it, do some preventive maintenance, and I would reference this NEMA AB4 document to give you guidance on what you can and can't do with a multi-case circuit breaker. You don't want to be taking it apart at all to look at those arc chutes and contacts and all that jazz. I know it may be tempting to do that, but that would not be a good thing. Trying to think of what else. So that's what I would do. In your case, I don't even think I could give you advice other than perform some maintenance. In fact, you can even look at this in this document in the outline. I'm 50-50 here. Geez, oh man. So look at this. It has test procedures. You have an insulation resistance test, an individual pole resistance test, and millivolt drop. So you can get a little view inside that circuit breaker by doing some tests without taking it apart. If you get questionable answers on some of these tests, then yeah, I would replace the breaker. If you want to send it back under warranty, if it's still under warranty and depending upon the manufacturer, leverage that as much as you can. Another benefit of buying through a qualified and identified distributor of our products and any manufacturer's products. So that's what the advice I would give for that question. All right. 170 amp or 175 amp? I'm not sure what that is referenced to. I'm not sure what that's reference to. 170, 171, whatever it takes. Power. Thanks, Robert. Carl, you're kind of new to the program, aren't you? I don't know that I've seen you chatting it up before, and I appreciate you being around. I don't know that I can remember a Carl Lewis. Let's do this. Yep. Hey, Tom, New York City, most 8-floor mixed-use buildings have 4,000 amp. Woo! 3-phase. 120 208Y service transformer feed the switchgear and protected by an insulated case circuit breaker as the main. Now that is tremendous. Think about that. 4,000 amp main. And I'll bet you, New York City, I remember one time I asked the chief electrical inspector, I'm going to go back, I'm not going to throw names. I said, what's the maximum available fault current that you have in downtown New York? And he said 200,000 amps. He says, do you want to know why? I says, well, yeah, I know why. I says, because you have parallel transformers, a secondary network. He goes, no, because you don't make anything bigger. So, Carl, with that 4,000 amp 3-phase 120 208 service, I know there's a lot of amps associated with that as well. Arc chutes on MCCBs. Yes, there are. Yes. Question on AIC rating. AIC rating of the breaker. It should be able to withstand this. But does the AIC rating mean once opening on the higher end of the fault that I can still be put back into service? Chris, my suggestion is if you know you hit, this is Tom speaking. If I know I had a very high fault current, I would take that breaker out, follow NEMA AB4. I would put it through the ringer just to make sure that that device, you may see information that says, well, you could take one hit. I take a hit on a breaker, especially once you do your troubleshooting and you know it was a short circuit, you can estimate what the value was. Chris, my suggestion, plop another one in there, take that one out, take a look at it, run through the NEMA AB4, what you can do, and then maybe use it as a backup for later. But I would just feel comfortable knowing, because I a lot of our guys and gals out there rely on that for arc flash calculations and all this other good stuff. That's what I would do. And again, that's just me talking. That's not Eaton or anybody else talking. It's just Tommy D talking to you from his basement. Hey, thanks, Felix. I'm glad you got something out of it. And we are at the top of the hour, I believe. And I've got to run. Being below the AIC rating guarantees an open, but does not guarantee it can be put back into service, correct? That's what I would say, Chris. That's what I would say. I would put it through NEMA AB4. I can go through the standard and tell you how it's tested, what I feel comfortable whether, and I can give you a comfort level on my personal opinion of things. But I would say you need to get it. You need to reconcile it in your own head with your own knowing what has happened at your facility, knowing the overall scenario on whether or not you feel comfortable putting that puppy back into service. That's just where my head's at. But I think we're both talking the same language. Joe Bellantoni, thank you, sir. Appreciate you dialing in. And Laurel, thank you very much. And everybody out there, thanks for tuning in. Thanks for doing what you do for electrical safety and for the electrical industry and IAEI. Hopefully everybody out there is an IAEI member. I am an IAEI member, and I'm proud of that fact. I'm also an IEEE member. Proud of that fact as well. So please contribute back and give back to the industry through both of those organizations if you can. You don't need to be an electrical engineer to join IEEE, and you don't need to be an electrical inspector to join IAEI. Hey, Carl, thank you very much. And I haven't seen you I'm glad you're engaging, and I appreciate your input, valuable input, and thanks for using the videos. I do this stuff. People ask me, why the heck do I do it? I don't know. And, you never know. You may save a life out there. You may do some good. And Mohammed Jafari, thank you. And I saw a note up above I think I missed. I think you said, hold on, where are you from, Mohammed? Boy, there are a lot of you guys are chatty today. I love it. Mohammed, I thought I saw Mohammed. Man, I can't find it, Mohammed. Wow, look at the comments. You guys are awesome. Can't find it, but Mohammed, I can't remember where you were from. I think I saw Iran in there, but I'm not sure. Man, being within the rating, it's supposed to fall in the safe manner, and it isn't prudent. Thoroughly test evaluator, simply replace it. Yes, Steve, I like your thing. All right, Nihad, thank you very much. You know what? Bobby Joe, my wife told me this before. She says, you say goodbye 3 or 4 times. This is my final time. Thanks, everybody. Thanks for what you do for electrical industry. Thanks for what you do for electrical safety. Please stay safe, and please stay healthy. And thanks for joining from Iran. Really appreciate it, Mohammed. And hopefully you get value out of this. Take care.